Good afternoon, everyone. I'm Mingma from Dalian University of Technology and a youth editorial board member of Smart Materials and Devices. It is my pleasure to welcome you to the Young Scholar Forum. This series was established to provide an inspiring platform for early career researchers to present pioneering work, explore emerging technology, and foster academic exchange and collaboration. Today, we are honored to have Dr. Guolin Yun sharing his work on multiscale structured liquid metal elastomers for 3D force sensing array. Before introducing our invited speaker, let me briefly introduce Smart Materials and Devices. Founded in November 2024 as an international gold open access journal, SMD published quarterly and follows a rigorous single-blind peer review process. With an initial target impact factor of 7, the journal aims to establish itself as a high-impact academic platform for research in smart material and devices. Accepted papers are free of APCs until 2029, and the journal also offers initiatives like annual Best Paper Awards, Frontier Forums, and Scholar Interviews. Here, you can see our official accounts and contact information. Feel free to follow us to stay updated with the latest research, journal news, and submission opportunities. This page shows the aims and scopes of SMD. The journal focuses on smart materials and devices, including areas such as smart sensors, wearable technologies, energy devices, and AI for materials. We welcome articles, reviews, and perspectives in these areas. The QR codes will take you directly to the journal website, and we warmly encourage you to explore SMD and submit your work. SMD is proud to be guided by a dedicated editorial leadership team. The journal is led by our editor-in-chief, Professor Guolin Yun from Nankai University, a fellow of the Royal Society of Chemistry and a highly cited Chinese researchers, together with 6 associate editors who bring expertise across smart materials and devices. Their leadership ensures that SMD maintains high academic standards and continues to reflect the latest advancement in smart material research. We are honored to have their guidance in shaping the academic vision of the journal and fostering a vibrant research community. To ensure the highest academic quality, SMD is supported by an international editorial board, currently composed of leading scholars from diverse regions. In addition, our youth editorial board engages rising researchers to contribute to the development of the journal and promote interdisciplinary exchange. SMD continuously expands its editorial team and welcomes outstanding scholars worldwide, including early career researchers, to join us in advancing the frontiers of smart materials and devices. Your contributions and collaboration are warmly encouraged. In addition to regular submissions, SMD actively organizes special issues around emerging research topics and application areas, providing researchers with an important platform to explore specific themes in depth. Currently, we are collaborating with the 19th International Conference on Electrorheological Fluid and meteorological suspensions to launch a conference special issue, strengthening academic connection and promoting international exchange. We warmly welcome researchers to contribute, and all submissions to these special issues will be free of article processing charges, offering an excellent opportunity to showcase high-quality research in SMD. SMD is also actively planning future sections, including academic forum, scholar interviews, and other engaging content. These initiatives aim to promote academic exchange and help high-quality research in diverse and interactive ways. Now, let me briefly introduce today's speaker, Dr. Guolin Yun, a professor at the University of Science and Technology of China. His research focuses on multiscale structured hybrid of filler elastomers with the embedded liquid metals and their applications in flexible sensor and stretchable electronics. He had already made significant contributions in this field, with numerous publications and citations. Please join me in warmly welcoming Dr. Yun to share his exciting work on multiscale structured liquid metal elastomers for 3D force sensing array.
Hey, thank you. Thank you very much, Professor Marnin, for your warm introduction, and thank you very much for the SMD editor board for the invitation. Okay. Sure. I think you can all see my screen. Cool. Okay, let's start. So thank you again, Professor Mar, for your introduction. And hello, everyone. My name is Guolin Yun. So today I will introduce multi-scale structured liquid metal elastomers and their application in the 3D force sensors. Okay, let's skip this page as we already made the introduction. And first, let me briefly introduce the conductive elastomers as a background. So I think most of you already know very well with conductive elastic composites. Well, this kind of composites are generally the elastomer matrix, like the different polymers filled with conductive fillers, like the carbon, metal, or conductive polymers. And they combine the high conductivity of metals or carbon materials with the high flexibility of polymers. And in those composites, the conductive fillers affect both the electrical and mechanical properties like the conductivity and sensitivity, while the elastic matrix mainly determines the mechanical properties of the composite, like the elastic modules, the tensile stretchability, and also the chemical resistance, and so on. Well, now I will briefly introduce the composition and the applications of these composites, basically focus on the force sensing composites. The conductive fillers are generally metal, carbon, or conductive polymers. For the metal fillers, they usually show high conductivity, both electrical and thermal conductivity, while the carbon fillers show good mechanical strength and also chemical resistance. Well, the conductive polymers, they usually exhibit much better flexibility than the above metal or carbon fillers. And for the conductive composites, their application basically depends on the response of their resistance to external load, such as force and strain. For instance, for those composites with constant resistance under loading, like compression or stretching, they are usually being used as electrodes of the flexible circuits. And for those composites with extremely high strain or force sensitivity to the external load, they can be used as different kinds of sensors. For example, used as pressure sensors on the wristband to monitor our health signals. And also, above this, currently, there are also many functionalities being introduced in the composite. For example, they can be used as wearable heaters and with different functionalities such as energy storage and use as transistors. Okay, so talking about the strain and force sensitivity, the sensitivity of composites is mainly dependent by the geometry of the fillers. Not the only reason, but that's the main reason. So those fillers usually have four main shapes: the particle, flake, wear, and stretchable or liquid fillers. So for the particle fillers, like the spherical metal particles, when the composite is stretched, those particles will separate from each other, so resulting in, show this here, so resulting in a sharp increase in contact resistance and also high sensitivity. Well, for the flake and wear fillers, they can overlap in the composite to form a connected conductive filler network to remain a basically stable resistance, so much lower sensitivity. And for the stretchable or liquid fillers like the conductive polymers, not that stretchable, but much stretchable than the metals, and also the liquid metal, usually the gallium-based alloys. They are purely liquid, so in theory, shows extremely high deformability and conductivity. So those fillers can deform along with the polymer, with the composite. And usually those kind of composites can even show stable resistance during stretching, and therefore can be used as a circuit or electrodes in the flexible electronics. Okay, so in recent years, the gallium-based liquid metal alloys are often used as fillers, secondary fillers in the conductive elastomers due to their high conductivity and high deformability. Previous works usually use those liquid metal fillers to reduce the resistance in the composite during stretching. For example, we can see in this previous work, the liquid metal can bridge the silver flakes to repair the conductive network during stretching. So in the right figure, we can see without liquid metal, under stretching, during stretching, extreme resistance increase without liquid metal, but with liquid metal, much stable. But after all, even use the liquid metal, most of those composites still show worse conductivity under stretching, which means even with the liquid metal, under stretching, the resistance will still increase. And finally, at one limitation, we will got insulate. So in summary, there are two main challenges in current work about the force sensing composite. So first, the resistance of most conductive composites increases during stretching, which is undesirable for application in super stretchable devices. And secondly, for most of composites, they are filled with only one type of filler and have no structure design. So those single filler composites usually face issues in mechanical and electrical properties, such as low sensitivity, the poor stretchability, and limited functionality. So to address these issues, in my work, I focus on 2 points. So first, I developed a new family of liquid metal composites filled with hybrid fillers of solid particles and liquid metal. This solid-liquid hybrid network achieves unconventional strain response, which means the resistance of these liquid metal composites can decrease by several orders of magnitude under any mechanical loadings. In addition, we also designed the multiscale structures from nano, micro to macro scales in the composites to achieve excellent force sensing performance. So those composites show several demos in soft electronics, including the flexible sensors, self-sensing actuators, and some wearable devices. Okay, now I will introduce some of my previous works as a background of my current research. First is the liquid metal hybrid composites, the start of all my research. So in here, this work, I developed this hybrid filler composite with unconventional electrical properties. We can see figure A shows the 3 raw materials of this composite: the PDMS matrix, iron particle, microparticles, and the liquid metal. Here, the liquid metal I use is a gallium indium alloy with a melting point of about 16 degrees, and it's liquid at room temperature. So onto the liquid metal and solid particle hybrid failure network, the composite shows anisotropic, shows unconventional strain response, which means you can see from figure C. It shows a maximum resistance at the relaxed state and under any mechanical loadings, including compression, stretching, bending, and twisting. Its resistance can always be decreased by several orders of magnitude, which is very unconventional response. So here the simulation result explains this phenomenon. We can see, so first, this composite has a positive Poisson's ratio about 0.4. So therefore, it will always be compressed in a certain direction under any mechanical loading. For example, here, when this composite be stretched horizontally, due to its positive Poisson's ratio, it will always be compressed vertically, which means along the y-axis being compressed. So we can see from the figure C and D, even under stretching horizontally, the distance between the ion particles and the liquid metal droplets, here the droplet A, B, and C, and the little circles between the ion particles, the distance between them decreased compared with the relaxed states, which decrease the contact resistance between those conductive failures. And also, in addition, the liquid metal can deform along with the polymer matrix and remain contact with surrounding ion particles to remain good conductive failure network. This can avoid the resistance decrease caused by the separate of ion particles, which means in this composite without a liquid metal, the stretching will increase the resistance. But now with the liquid metal, the overall resistance of the composite can decrease sharply under any mechanical loadings by more than thousands or million times. Okay, so after that, I focused on the microstructure design of these composites. So here I created a microstructured composite with anisotropic failure networks. This composite is solidified in a strong external magnetic field. So in this way, we can see the ion particles can form chain structures along the magnetic field direction. We can see from SEM and EDS image. And with the liquid metal droplets between them can form this anisotropic failure network. So this impacts the composite with very special anisotropic strain response. Here, when compressed along, we define the angle between the measurement direction and the failure alignment direction as theta. When theta is 0, which means compress the composite along the failure chain structure direction, it shows normal response, which means under compression, resistance decrease, normal response for sensors. However, when we compress the composite perpendicular to this direction, when theta is 90 degrees, compress it along the direction perpendicular to the chain structures, the resistance of the composite can increase during under compression. So that's very interesting. So by adjust the anisotropic degree of the composite, we can achieve this phenomenon. We can see in figure E. Achieve this, which means at the 0 degree in this direction, it shows very high sensitivity to the external force, so good censored. And in the direction of theta equals 90 degrees, perpendicular to that direction, it can show consistent stable resistance. So in this way, the force sensors can ignore the horizontal force applied on it. Therefore, solve the problem. Therefore, this sensor can only detect the normal force applied on the sensors. And next, I focus in addition to the microstructures, I also studied the surface structure design on the composite to further improve the force sensing performance. Here, I created the force structures on the composite film. We can see the grouped structures, and under pressure, the stress concentration on the surface structures can produce a greater strain. As we can see in the force simulation. This can result in a lower resistance and higher sensitivity. From this curve, we can see the composite shows extremely high pressure sensitivity. with at 100 kilopascal, its conductivity can increase by more than 100 million times. And more importantly, this composite can maintain the high sensitivity under high pressure. I believe most of you know many papers on the high sensitivity force sensors based on the surface structure design. Like usually their principle is, so under pressure, the contact area of these surface structures increase. The contact area increase, resulting in lower decreased resistance and improved sensitivity. But the disadvantage about this design is that at high pressure, their contact area tends to be stable, and the sensitivity drops significantly to nearly zero. But our liquid metal composite does not rely on the contact area, because this material itself has extremely high sensitivity, as I introduced previously, thus can avoid this problem. So based on this structured composite film, I developed this flexible pressure sensor for the narrow measurement range. So it has a high sensitivity up to 30 per kilopascal, as well as a low detection limit of only 2 to 5 pascals. Okay, so next I will briefly show a simple demonstration of these liquid metal composites in the force sensing technical. So here is the demonstration of the a force sensing wristband based on the composite. So we developed the gesture intention recognition system based on this wristband. This wristband can worn on the arm, so to detect the tiny muscle tension generated by the finger movement intention. And here, therefore, we can distinguish the different gestures through the signals from the sensors. And we selected two sensors, sensor 4 and 7, to train a machine learning model and achieve the gesture recognition accuracy of over 95%. And finally, we demonstrated its function in a robotic arm remote control system. And more importantly, our gesture recognition system is worn on the arm, not on the hand. So it can be used for people with hand disabilities, showing its great potential in artificial limb control. Okay, so now I will talk about my current research. Finally, the main topic, the multi-scale structured 3D force sensing array. Okay, so first about I'm briefly talking about the background of this research. Why do this? So my current research focuses on developing a micro sensor array with 3x force sensing abilities. At present, we know most of flexible force sensors they show low sensitivity or narrow dynamic range. And that's one part. And also, they usually cannot detect the force directions, which means they can only know, okay, how large is the force applied on it, but they don't know where where is the force applied from, the force direction. And although some do have some triaxis force sensors published in recent years, but they still show the large dimensions and resulting in low spatial resolution, as we can see from the right figure. Currently, the state-of-art size of the 3D force sensors is still 1 unit, is still 1 millimeter. And however, the high sensitivity and high spatial resolution 3D force sensor, these abilities are crucial for current environmental interactive devices, such as artificial limbs or intelligent robots, because they need such abilities to detect the complex tactile information to achieve the flexible movement and operation, and to recognize complex the information like this, the force directions and the surface roughness, stiffness, sliding states, and so on. That's why they need this 3D force sensing. So in bridging this gap, in this work, we created the multi-scale structured 3D force sensor array. It can not only decouple the triaxis forces with high sensitivity, but also achieve the high resolution, spatial resolution of only 300 microns. Okay, so here we can say from figure A, this work basically combine the 1, 2, 3. Yeah, 3 or 4 works I just introduced above. This is based on this, the liquid metal composite with this multi-scale structure design. You can see here, you can see the liquid metal composite and with the anisotropic structures. Here I introduce the porous structures to further improve its sensitivity and higher flexibility. And also, this design is I introduced the pyramidal structures on the composite. This structure design can use the stress concentration to further improve the force sensitivity of the composite. We can see here it's achieved the even higher sensitivity of more than 100 per kilopascal due to this pyramidal structure. And then except from this high pressure sensitivity and wide measurement range, this structure, more importantly, the pyramid structure can also decouple the normal and shear forces. That's the key of this work, and therefore it can achieve the 3D force sensing. So as we can see from the figure D, here I designed 4 bottom electrodes on each sensor unit. Here is a single pyramid sensor unit and 4 electrodes on bottom. So according to the simulation above, the bottom pressure distribution in figure B, we can see under the normal force, the pressures on the 4 electrodes is equal. But when there is only a shear force, the bottom pressures on the electrodes on 2 sides, for example, electrodes 1 and 2 and electrodes 2 and 3, the pressures on those electrodes is opposite. So therefore, the normal force is proportional to the average pressure on the electrodes, and the shear force is proportional to the gradient of those pressures. Therefore, we can use these 4 electrodes to measure the bottom pressures and then calculate the normal and shear force applied on it. And also, here, figure C shows the basic principle. Since the liquid metal composite is very sensitive to the force, so it can measure the pressures applied on each electrode with high sensitivity. Okay, so in addition to measure the force and the directions, this sensor can also detect the complex contact information, as I said before. So through the changes in triaxis forces, including like the sliding state and roughness of the contact surface. Here I show these 2 functions. So from figure A, we can see when sliding occurs, the shear force on the sensor unit will immediately decreases, because the friction ratio, fraction factor between the static and movements fraction factor is different. That's why the shear force will decrease suddenly, while the normal force remains basically stable. In this way, it can recognize the sliding state. And also, in following movement, the tip move on the surface of the contact surface, rough surface, will lead to the tip vibration. This can cause a signal change, and from those changes, we can calculate the surface roughness of the contact surface. And our next step is to improve the spatial resolution of our sensor array. So here we prepare the miniaturized 3D full sensor array based on this micro-sized sensor unit. Here is the photograph, and here is the SEM image. We can see from it the sight lines of the single macro sensor unit is only 200 macros. So the prepared sensor array shows a high spatial resolution of 300 macros. It can therefore be integrated has the potential to be integrated into robotic hand to achieve the tactile sensation capabilities comparable or even surpass the human fingers. So this video demonstrates how the pyramidal sensor unit decouples and detects the 3-axis force in real time. we can see to show it clearly, we use a large unit with set length of 4 or 8 millimeter, a large one to show it clearly. So we can see that when the force is applied on the unit, the 4 bottom electrodes can measure the pressure distribution, and therefore it can quickly calculate the component of 3 exercise forces. Can see the normal force and the shear force along x and y axis. Yeah. So, in summary, in this work, we created the 3D force sensing array with a high spatial resolution and sensitivity, and also wide measurement range, as well as sliding and roughness detection abilities. We believe such a micro sensor array has a potential to bring the human tactile sensation to force sensors, and therefore can promote the development of the artificial limbs and intelligent robotics. Okay, so finally, I would like to thank my supervisors, collaborators, and my students for their great help in my work. The QR code above is my personal homepage. You can please feel free to scan it if you want to learn more about my research details. Okay, that's all. Thank you very much for listening. Please feel free to ask any questions.
Thank you, Dr. Yun, for the fascinating presentation. Now the floor is open for questions or some comments. Who would like to start? If you have questions, please feel free to unmute and ask, or share your question in the chat box in English or Chinese. Dr. Yun, actually, I have a question. That was a great talk.
Okay.
I have a question myself regarding the materials fatigue performance. What is the materials performance in terms of long-term stability and reliability under extensive cyclic testing?
Okay, so. Okay, thank you. Yeah, that's an important question. Sorry, I didn't show the plot here. Okay, so of my previous research, including the first liquid metal, the sensors, and also the 3D force sensors, I did the cyclic tests on it for about, currently, I did the 20,000 cycles, 20,000 cycles loading tests on the sensors. So I can't say it has perfect stability, but usually says, we know in the composites, especially for the pure resistance for sensors, we always have a problem, which is resistance shift, which means we put the resistance here, we measure it today, the resistance showed like 100 kilo ohm. So after 1 month or 1 year, we measure it again, it can be 200, 300, or even 1 million ohm. That problem also exists in my composite. That's why, also this one question. Also, another part is during cyclic tests, the resistance also changes. So for this part, for my composite, in the cyclic test for 20,000 cycles, in the first hundreds of cycles during testing, the initial resistance will be increased at the first 100 cycles, but after that, it tends to very stable with a change below 0.1%. So that's, I can say that's part in the long-term test that's very stable. But also for the resistance shift I mentioned above, which means I put the sensor here, measure it once, and after 1 year, I test it again. The initial resistance always increase. To address this problem, I always use, that's why in my design system, in my sensor system, I will use calibrate, which means before measurements, my program will automatically measure the initial force of the sensor and use it as a new initial resistance. Because for my sensor, each time if you add the same pressure force, for example, I add 0.1 Newton on the sensor, the resistance decrease, for example, by 10 times. So even after 1 month, 1 year, 1 Newton applied on it, it will still decrease by 10 times, no matter what the initial resistance is. So by collaborate the initial resistance, I can ignore the resistance shift. So it can, the stability of the sensor system itself is quite stable. Yeah, thank you.
Thank you. I have another question about the flexible sensor. If such sensors are used in wearable devices or robotic scheme to achieve intelligent grasping or other fine operation, will there be issues with energy supply problem or conformal adhesion to complex curved surfaces? If so, what are some potential solutions?
Okay, yes. So that's also very important and good questions. Thank you. So I can answer the first question. So about energy supply. Well, it depends in two situations. For simple wearable devices and in robotics, we know usually in wearable devices, for example, soft electronic wristband, we usually work on wristband to monitor very simple sensors. Usually, each wristband only have less than 10 sensors to measure like the temperature, the blood pressure and the force. Basically, that's all. And the humidity. Yeah, usually that's all. So it don't have a large data transfer and processing requirement, and with easy data transfer. So in that case, we don't need to high power supply. And I know currently there are many, before 10 or decade years ago, the people have idea called the self-power, right? The friction nano generator. But until now, I think that technical is still not well development. It's still developing. So compared with cell battery, it shows not that good stability and cost. It's usually not cost effective. So in my device, for the wearable devices, I still use the cell batteries to power the wearable sensors. And for the data transfer, currently we can use the wireless transfer like the Bluetooth to transfer the data to phone. That's very easy. And for the second phenomena, not phenomena, sorry, for second application in the robotic hand or artificial legs, usually those devices have in-suit batteries with high power supply. And also in those cases, for example, current commercial force sensors on a single robotic hand, they can each finger, robotic finger can have up to 100 force sensors, and the data transfer for each finger sometimes can up to 1 million bits per second, and that require a high power. And also currently in the intelligent robot hand, sometimes they have inbuilt machine learning chips for each sensor in the robotic hand, which means even though the power for those chips is much lower than the phone or PC chips, but they still require high power supply. So in this case, you usually use wire power supply from the robotic itself. And that's for the power supply. And I think your second question is about the adhesion on curved structures, right? Yeah.
Yeah.
Yeah, the second question. Yeah, okay. So for that question, you can see this figure currently. So if we want to use this sensor as a flexible flexible electronic skin on robotic hand, that's require 2 points. So one is a flexibility. Many people research on this. That's basically not very hard because we can just decrease the thickness of the device. We can in this way we can address this. For example, currently for my device, I can decrease the thickness to the limitation is not very thin, 100 micrometers, because my technical is not that advanced. I know in some group, they can achieve the total thickness of the sensor device is lower 10 microns. That's very thin. So for them, the flexibility is not a problem. Any curved surface they can warn their cover their sensor array on the curved surface. But talking about the wearable devices or soft robotics, another question is a stretchability. That's a more important question in my opinion. Especially currently, we usually use, for example, the soft robotics. They have a soft hand, and the people they have the junctions, and in this case, we need the pressure sensor or soft sensor electronics devices to be super stretchable. So current Therefore, the current solution is not very suitable. Currently, for example, the electrodes. My current solution uses evaporation, no matter thermal or electron beam evaporation. I evaporate the gold electrodes on the surface of my device. Those electrodes can only stretch under about 10%. If under higher under higher tensile strain, the electrode will break and cause electrical connection failure. So currently, people use a new technique, not very new, but developed also for years, called 3D printing for the soft electronics. They have some commercial available stretchable conductive ink made from the metal ink, but with polymers inside. So the printed circuits is very stretchable, and currently they can print. I know they can print 1 micrometer wide conductive wires. That's very amazing. So I think that's a solution if we want to use this thin film on the curved surface. So if we can use this to address the flexibility and stretchability, the next step is to try the best to remove all the rigid part in the composite. Actually, for current design, for example, in my research, the composite itself is soft. It's 100% soft. And next step, I will introduce the 3D printing of the conductive inks on it to print the stretchable circuits patterns, and then just the whole sensor device can be flexible. But also, still one thing is how to the interface between the soft devices and the rigid part. For example, the robotic. The interface between the soft and hard the soft-hard interface is another problem, especially during repetitive use. For long-term use, the interface failure will be a major problem for the soft electronics. Okay, thank you.
Thank you, Dr. Yun. It's a fascinating answer. Let's see what else questions we have. Well, it looks like there are no further questions. Maybe we are all digesting this insightful results. Okay.
Yeah, I think most people on the online should not in Zoom meetings.
Yeah. If your question wasn't answered or you just thought of a new questions, please feel free to contact Dr. Yun after the forum.
Yeah.
I know he
You can scan this QR code to contact me or know more details. Oh, sorry.
Okay. It looks like there are no further questions at this time. On that note, let me thank to Dr. Yun again for a truly excellent presentation and for his insightful answer to the questions. And thank you all for your active participation. We look forward to your submission or seeing you at future events. Thank you.